Okay, so what we're going to be going over here, guys, okay, just going to quickly explain the lab. We'll do the usual things we do at the lab. We'll talk about the design, the hypothesis, okay, all of that stuff, and then we'll talk about the procedure. The procedure is actually really, really straightforward, okay? It's, as long as you follow the instructions, it's virtually impossible to mess it up, all right? So, the problem we're investigating here is how can we determine the amount of work that's done on an object? The object we're going to be doing work on is going to be the rubber bands. All right, we're going to have them stretched between the legs of two desks. All right, everybody follow me there? Not between one desk. It's too far. These won't stretch that far. Okay, so we're going to put them between the legs of two different desks, and then we're going to pull on them with these. Okay. These are spring scales. They're supposed to read force. The picture on the box shows a scale that has newtons on it, which are the units for force. Unfortunately, what is in the box is a scale that has grams and ounces on it, every last one of them. Okay? So when we called the supply company and said, "You didn't send us what we ordered," they said, "Yes, we did." We said, "No, you sent us the boxes for what we ordered, but what was in the boxes wasn't what we ordered." They said, "Tough, you know what." Okay, so we're stuck with them. On the good side is it's actually not all that hard to convert grams to newtons, and I'm going to show you how to do that, okay, when you're using these. Now, one of the things you will have to watch for is that the little scale here can slide up and down, all right, and we want to make sure that when there's nothing hanging on the scale, the little measuring tab is at 0 so that we get good, accurate results. Okay, everyone follow me there? So just double check that, okay, when you get yours. You also want to make sure that you get, okay, the 2,000 gram ones. All right, they're labeled. The boxes have a 2,000 or a 500 on them. If the one you pull out of the box is green, you have a 500 gram one. You want a 2,000 gram one. Okay, everybody with me there? All right. All right. So. Identify, explain, manipulative, responding, and controlled variables. Well, you're going to be building this graph that you can see over here, okay? And we can see that the two main variables of this lab are distance and force. Now, we're going to choose the distances that we stretch the rubber band to. Since we are choosing the distances, distance is the manipulated variable. You're welcome. Okay, you need to explain a little more than that, obviously. What is responding to that is what is read on the scale. Okay, what is read on the scale is the force being applied to the rubber band. All right. Controlled variables. Okay, you guys can look at the procedure and figure out what the controlled variables are. I would say anything that could contribute to tension in the rubber band should be identified. All right, everybody follow me on that. One of the key things you need to make sure of while you are doing the procedure for this lab is that the desks that this rubber band is attached to do not move during the experiment. If they do, it is possible that there would be a stretch or a slackening of the rubber band in the middle of the experiment, and that will change your results as you go along. So it is advisable that you have a group big enough that there's a person to measure, a person to pull with the scale, and two people to sit in the desks so they don't move. All right, okay. All right, so there's our variables. You guys can do the explaining. Hypothesis. Generate a hypothesis that explains how, using the materials below, we can calculate the work done on an object. So our if part here should probably talk about how we calculate work. Agreed? How do we normally calculate work? Work is what two things? Force times distance. Right, okay? I would say that that probably needs to be incorporated into the if part of your hypothesis. Now, the and part is going to describe your experiment, same as it always does. Okay, this is kind of your picture here of what you're going to be doing. All right, you can describe that in the and part. Okay, the then part should probably talk about your graph. Okay, now looking at your graph here, all right, you've got distance and you've got force. And we already know that for work, you need to multiply those two things together in order to get work. All right? What you'll have to do is, using the analysis, figure out how you're calculating work. You can put something in the then part of your hypothesis for now, and then in your conclusion, if it wasn't right, you can say, I do not accept my hypothesis. I reject it for these reasons. This is how work was actually calculated in this experiment. All right, everybody with me there? It is absolutely okay, to not have the right then in your hypothesis. Right? In fact, in real science, more hypotheses are rejected than are accepted. Okay, and I mean a lot more. Like 95% of all hypotheses are not fully accepted. Okay, that's how science keeps going. Right? We revise and try again. All right. So for the procedure, we're going to have the desk here. You're going to have your rubber band set up. It gives you some suggested distances, but I'm going to advise that you make a slight change to that and do this. Put the rubber band between the two desk legs. So if you can see here, there's not a lot of space between these two desk legs, and you probably don't want a whole lot more room than that. Just enough so that the rubber band isn't slack. Okay, so pull them far enough apart that it's just taut. Everybody follow? Okay, then put two people in, or put a person in each desk so that it can't move. Then you're going to take a meter stick, you're going to put it right in between the two so that it reads 0, all right, on the back edge of the rubber band. Now, what you're going to want to do at that point is do your maximum trial first. Okay, so you'll hook this thing onto the rubber band and pull it until you max out the scale. Pull it right to 2,000 grams. Okay, everybody with me there? And record that distance. All right, whatever it is. Then pick 3 or pick 4 other distances. Yeah, let's say pick 4 other distances that are shorter than that. Okay, and record your numbers for those. Everybody got it? That way, you don't end up pulling it to the point where it's beyond the elastic reach of the rubber band or beyond the scale. Okay, everyone follow? So you're going to do your biggest one first and then kind of go down from there. Yes? Okay. So when you're doing your results here, this is kind of what you're going to have. Okay, you'll have your grams on the scale and it'll look like this. Okay, just like the one I'm showing you here. Now, what you do, is divide this number by 100. Okay, it's close enough for what we're doing. Okay, that will be your number in newtons. So if it reads 400, you're actually using 4 newtons of force. Is that an easy conversion? All right. Okay, you'll need a chart that looks like this. Okay, you'll have your distances in there. Okay, 0.05 meters. That's 5 centimeters. Okay, make sure this is in meters, guys. Okay, so 0.05 meters, 0.1 meters, 0.15 meters, 0.2, 0.25, whatever. Okay, so how many have we got here? 1, 2, 3, 4, 5, 6. Let's go with 6 different distances. Okay, we'll ignore the bottom one here. Okay, so do your maximum one first, whatever that happens to be. Okay, then do 5 others, and then you'll have good data from there. All right, questions on how the procedure is going to work? Okay, you need to make sure that you do this just like the diagram shows and that you have both sides of the rubber band in the scale. All right, don't just pull one side of it. You want to pull both sides of the rubber band together. That's why we're measuring from the back side of the rubber band. Okay, so exactly like this setup. All right, when you get your data in, then you can start on your analysis. Okay, we calculate the area beneath a force distance graph using the equation for the area of a triangle, 1/2 base times the height. So do you need to draw a best fit line on your graph? Yes, you do. Okay, you can't find the area of something if you don't have a line for it. Okay, so you will need a best fit line on this graph. Make sure that you draw one. Use Excel. Okay, because you're handing this in on Google Drive, same as always. Okay, so get it to draw it for you. Then do the calculations for the area underneath the line. Okay, a lot of this here is explanation, but it doesn't really matter. Just make sure you do this area calculation here. Okay, what does the area under the force graph represent? How do you know? Okay. I'm going to give you a little tip on here. Okay, look at your units. Look at what you multiply together when you do that. Okay, see what it gives you. Look at what things you're multiplying together when you find the area of that. All right, everyone follow me? Gives you a tip for answering that one. Okay, for number 1, I just want to see your calculations. Okay, you can type those in on the calculator because they're nothing terribly complex. Or sorry, type them in on the computer. They're nothing terribly complex. Then you got your conclusion and evaluation, same as always. Don't do the class discussions. We'll talk about those when I've marked the labs and handed them back. Are there any questions? Okay, due date for this. I'm thinking May the 20th. Okay, so May the 20th is going to be the due date for this. That is the day after we get back from the long weekend, I believe. All right, not the day after the long weekend, the day after the day we get back from the long weekend, I think. Okay, May 20th is the day. Doesn't matter what day it is. Okay, May 20th is when it's going to be due. All right, so there are no questions? All right, so each group needs one 2,000 gram scale and one rubber band. Guys, I don't want anyone to lose an eye today, so please behave yourself. Okay? No snapping the rubber bands at anybody. Okay? All right, come grab what you need there, guys. Tip, one rubber band only. Should that rubber band snap at any point, like while you're pulling it, if it snaps during the experiment, start over. Controlled variables, guys. How do you know all of those rubber bands are exactly the same? Okay, so if your rubber band is to snap in the middle of your trials, you will have to do the other trials over again because you can't be sure about the other rubber bands being exactly the same. Okay? Right, reminder, because I've walked around and looked at a few people's charts, okay, and they do not look like this chart. Distance in meters, okay, force in newtons. So remember, divide your grams by 100 to get the force in newtons, okay, and take your distance in centimeters, okay. You gotta put that in meters as well by dividing by 100. Okay, you're dividing everything by 100, guys. Guys at the back, yeah, you might want to listen for this. Okay, if your chart is not in the right units, you will get 0 for your observations. So listen carefully, do it right. Okay, all right. All right, remember, guys, you're also going to get a force distance graph where you got to draw your best fit line. Okay, and do exactly what it says in the analysis. Okay, don't freelance. Follow the instructions in the analysis to the letter, and you're going to do all right on the analysis part. Okay, freelance, don't listen. Well, take your chances then. All right, make sure you do as it says.